again. So today we'll be talking about the energy module in the Year 11 chemistry syllabus. And in particular, we'll be looking at first-hand investigations for exo and endothermic reactions. Okay, so when we were dealing with exothermic, endothermic, and energy in reactions. So now we're going to look at the first-hand investigations that you sort of have to do to continue going through your HSC and your preliminary course. Okay, so there are a number of pracs that you can do, but the aims of these pracs are simply to observe practical reactions for these two, exo and endothermic reactions, and to learn practical lab skills. So lab skills are very important. Something that's a little bit overlooked in HSC, but they are very important, particularly if you want to move into a science field in the future. Having good lab skills is almost essential. So exothermic reactions, what can we do in the lab? So here's something that you shouldn't do in a lab. But one of the main, there's a lot of reactions that we can see that are not as explosive, so a little less exciting as well. But there are numerous ones. So the dissolution of sodium chloride is an exothermic reaction. That's one. The neutralization reaction. So when you mix an acid and a base, you get neutralization, which gives you a lot of heat out, which you can also study. As long as you use a fairly low concentration of acid, you should be fine. Metal-acid reactions, again, they release a lot of heat, and just keep the acid concentration low and you'll be very safe, because it does release hydrogen gas. So you don't want to have it too vigorous and then have a small explosion of hydrogen gas. And each of these reactions will produce a noticeable increase in temperature. So you'll actually see a very strong increase in temperature, okay? It'll be very noticeable. It won't be a very minor one. You will see a difference. So one way of doing this would be to use NaCl. So we measure 150 mils of water and place it in a styrofoam cup. And why a styrofoam cup? Well, we want to insulate it so that we can measure its temperature, okay? Place the thermometer in the cup and note the initial temperature. Just remember not to just read the temperature straight away, because it will fluctuate a little bit. Just give it sort of 5 minutes to adjust, because it is a bit of a slow process. And make sure the cup water is well stirred so that the mixture doesn't have sort of different levels of temperature, because we don't want any sort of problems. So then we weigh out 10 grams of sodium chloride and place it in a cup. Okay? So we place it in the cup with the water. Okay? So we pour that 10 grams into the cup. Then we mix till all the salt has dissolved, and then we observe the thermometer reading. Okay? Again, wait till it sort of settles, because the temperature will fluctuate as you mix it, because the water is moving at different temperatures. So again, just watch out for that. So you will note a temperature increase. So the temperature will rise slightly. You could use the same procedure with an acid and a base. Same sort of procedure. But you substitute the water for an acid and the salt for a base. So instead of using 10 grams, maybe use 150 mils of non-concentrated acid, or maybe even say 40 mils of more concentrated acid. And I'd probably suggest use a glass beaker rather than styrofoam, simply because we don't want to have any sort of unknown chemical reactions happening with the acid and base and the styrofoam. So glass, we know, is very inert, so that's probably a better choice. So with endothermic reactions, the reactions that we can do in a lab include the dissolution of potassium nitrate and the ammonia and water formation. Okay, so there's not as many endothermic ones that we can see, but if you think about an ice pack, what you do with an ice pack is usually sort of snap it or break it beforehand. And what happens is that mixes two chemicals together, usually urea and water. And what that does is that can suck out the heat in a particular area because it's an endothermic reaction. And so when you place it on your injury, it's actually removing the heat from your body, so you get that cooling effect. So that's what an ice pack does in terms of endothermic reactions. So it usually mixes two chemicals and you get a cooling sensation. So in terms of what we're going to do, we'll do the potassium dissolution, potassium nitrate or ammonium nitrate as well. So if you measure 150 mils of water and place it in a styrofoam cup, same as before, then you place a thermometer in the cup and then measure its initial temperature, again, same as before. So weigh out 10 grams of ammonium nitrate. So ammonium nitrate is our dissolution chemical at this point. And you place that in the cup as well, just like before, just like the salt. Mix till fully dissolved and you'll observe the thermometer reading. And you should note that the temperature has decreased. So what has happened is that when you've mixed the ammonium nitrate in the water, it's actually absorbing the energy from the thermometer, and so the thermometer has gone down. So the temperature that the thermometer sees is less. Okay. So that concludes today's lesson on the first-hand investigations that you'll do. If you haven't done them already, that's fine. This will be a quick overview of what's happening. If you have done them, this should be a revision. So remembering that there's many reactions that we can actually do in a reaction, in a chemical lab. And so these ones are the safe, observable ones that the HSC Board of Studies will permit. Okay. So we'll move on to the question segment and we'll see what we can learn from that. Okay, so for the metal-acid reaction between sodium and HCl, write the balanced chemical equation. Okay, so we've got sodium, which is Na, plus HCl. Now what does it give us? Well, when we look back at year 10, we realize that metals and acids react to give you H2 gas, hydrogen gas, plus some kind of salt. Okay. Now that salt is just a metal and a non-metal mixed together, or bonded together ionically. So we'll just put the H2 down first. Then we realize that all that's left over is Na and Cl. And I'm sure we've seen a salt similar to this in our lives already. So this NaCl is just table salt, so we're familiar with that. Okay. Now the next part is simply just to balance this equation. Okay. So we start with a hydrogen. We've got 2 hydrogens on this side and 1 hydrogen on this side. So the simple solution is just to put a 2 here. But what we've done is we've unbalanced the system even more now because we've got 2 chlorines and only 1 on this side. So again, we'll just put a 2 here to make 2 chlorines on both sides. And then again, we've unbalanced the system because now we have 2 NAs on this side and 1 Na on that side. So now we'll put 1, 2 here, and that is now balanced. 2 Na, 2 Na, 2H, H2 or 2H, 2Cl, 2Cl. So we're happy. Okay. And if I rub this out for you, you'll see that that's the correct answer. Okay. So in the case of balancing chemical equations, essentially what you're doing is you're constantly going back and forth till you get to the right answer. And in computational science, we call that iteration. So we kind of iterate or repeat the process until we get to the right answer. Okay. But yeah, okay. So that's how we balance that. So question B, why is the strong heat release from this reaction a concern in terms of lab safety? So why are we concerned about this? Well, because remembering that when you react an acid and a metal, you get quite a strong heat release because it's an exothermic process. And particularly Na, which is quite a reactive metal, will give you a lot more heat than, say, zinc or aluminium. So one of the major products of this reaction is H2 gas. So H2 gas, if you studied some history, the Hindenburg was full of H2 gas and it caught a blaze. And H2 is quite a flammable gas. If you put it in a car engine, or if you have a car that runs on H2, it's quite powerful, simply because the H2 burns really, really fast. And that's good for cars. So the strong thermal release, and ordinarily that would be okay. So if we just had hydrogen gas with no sparks, that's fine. But because this system below it is really releasing a lot of thermal energy because of this reaction here, we might see an unexpected ignition of the hydrogen because of all that heat, and that can cause a potential safety concern. Okay? So that heat from the reaction could actually light the hydrogen on fire, which would then be a very strong safety concern. So question 14, write the chemical equation for the dissolution of potassium nitrate and explain with respect to bond formation why the reaction is endothermic. Okay, so here we go. So we know potassium is K. And we know, we may or may not know this, but nitrate is NO3. Now the question is, we know that the valency of this is +1 because it's in group 1. When we look at the periodic table, K is in group 1, so its valence is 1. But what is the valence of this? Now often your schools will tell you to just remember it, and that's fine. But there is a way to calculate it based on how many electrons oxygen needs and how many electrons nitrogen can give. Okay, so nitrogen has 5 electrons in its outer shell. Okay, because it's in group 5, right? Oxygen has 6 because it's in group 6. Okay, so this is what the groups tell us. That means, and now I'm going to make a big assumption, that oxygen is only going to take in electrons. It's not going to give them away or share them even. So oxygen needs 2 electrons to make 8, right? You can see that. It's got 6 already, so it needs 2 more. So O needs 2 electrons. And it can get them from the nitrogen. But the question is, how many electrons does O3 need? Or 3 oxygens? Well, it would need 6. Right? Because there's 3 times as many oxygens as 1. So in total, the O3 system needs 6 electrons. Nitrogen only has 5 that it can give, right? And if nitrogen only has 5, it means it needs an extra electron from somewhere else. And so if it grabs another electron from somewhere else, what we'll see is that there'll be 1 more electron than proton, so its charge will be -1. Okay? Which means that its valence is -1. Okay? So you could have just remembered that, or you could sort of derive it this way. I just like the idea of deriving it this way because it means I remember less things, and that's good for me. So we can see that KNO3 is, so if we add them together, potassium nitrate is just KNO3. And we're putting it in water, and that will give us KNO3 in aqueous state. Okay, so we started with KNO3 solid, then we added water, which is really, really badly written, and then we get the aqueous form of KNO3. Okay, and there's your answer. But why is it endothermic? Well, the bonds between the ions in KNO3 are broken, and this requires energy. Okay, we know this. New bonds are formed when these ions bond with the water molecules. So when they've been freed, they now get surrounded by water molecules, which will then form new bonds, which will release energy. But the bonds formed release less energy than the energy needed to break the bonds. And so in total, you needed more energy to break the bonds than you got out. So it must be an endothermic reaction. Okay. So last question, question 15. Sodium acetate or hot ice is a chemical that can be prepared at home. So this is quite a safe thing to make at home. Just mix vinegar and baking soda, but not really rapidly, otherwise you'll get the science project volcano situation going. Just a little bit at a time. So when you've prepared this sodium acetate and cool it below its melting point, it can remain in liquid form. Okay, so I know that sounds really, really crazy that I can make it remain in liquid form until below its melting point, but it actually does stay that way for a little while. However, when it begins to crystallize, so if for instance you accidentally touch it and you start to form crystals, the crystals feel hot. Okay, the crystal you'll feel is hot. So explain why this might happen based on bonding and energy release. Okay, so if you want to see more about this, or you want to see some cool things about this, look up hot ice on YouTube, and you'll see lots of cool things. But here we go. This is how we answer this question. So the bonds between the sodium acetate in liquid phase, so liquid state, are rearranged, forming new bonds in the solid phase, or solid state. So as the sodium acetate crystallizes, new bonds are formed, releasing energy. Okay, so the new bonds are forming, releasing energy. This energy release gives the sensation of warmth when touched, despite its ice-like appearance. So it looks like ice, but it's actually warm. Okay? So that wraps up today's lesson on the first-hand investigations. So we've looked at the first-hand investigations for exo and endothermic reactions, and we've answered some questions on lab safety, as well as why the chemistry sort of works out the way it does for these reactions. So that concludes this section on combustion chemistry, and so I look forward to seeing you at our next lesson.